And depending on the number that you put here, right, it would definitely affect how you would come up with each of these here. So you could find some different ideas of how to fill it in. So we can come back and talk to it at the end. How many of you guys remember this format of division? Okay, and with the little r, and you know what the remainder was. But then once you basically learned how to write fractions, that kind of went by the wayside. We didn't really write it as remainders anymore. We're not going to do that, but it's important for us to recognize that vocabulary again, that piece that you had extra that you started writing as like 3/4 or 1/3 or whatever it was, that numerator of that was a remainder. So for example, you guys don't have to write this on your paper, but if we were to divide 6,324 by 7, just a little reminder of how this works. I know, kind of weird that we're doing this in our class, but we have a specific algorithm, okay, that we use to get through the process of division. So the first thing we try to do is we ask ourselves, okay, like, does 7 go into 6? Like, is there an integer, positive integer, so I guess like a whole number, I could multiply 7 by and obtain 6. That's not possible unless we use rational numbers like fractions. So we move on to look at 63, right? And so then we decide, okay, what integer will get me as close to 63 without going over to multiply by 7? And so we would choose 9, right? And so then once we figure out that value, we take that value, we multiply this quantity over here, right? 9 times 7 is 63. We write the product here, only underneath the portion that we were trying to fill it in with, and then we perform the operation of subtraction. Okay, 0. Then we drop down the next term, okay, and we ask ourselves the same question. What can I multiply 7 by to get 2? And in this case, nothing unless it's a fraction, so we go with 0. So technically that gives us 0, and then we have 2, and then we drop down. We have 24. How many times can 7 go into 24? Say like 3. 3 times 7 is 21. And then we get this 3. So when you were younger, you wrote like remainder 3, right? Then you started writing it as 903 and 3/7, right? This really means 903 plus 3/7, right? 903, but then not plus 1, that would take you to 904. 903 plus 3/7 extra, okay? So that's going to carry over into what we're doing, because we're going to take this exact same division algorithm that you guys know, but we're going to perform division with polynomials, okay? So we want to take 4x to the 4th minus 5x squared plus 2x plus 4, and we want to divide it by 2x minus 1, okay? So the process is the same. So we're going to set it up the same. Our dividend, sorry, I keep doing this, goes underneath the division sign. Now, I do want to be a little bit careful. This polynomial is written in standard form. What's the degree of the polynomial? 4. If you want to perform division, you want everything to line up right? And with our number system, that's pretty easy, because if we don't want a number, we put a 0 in that spot. Like if we want to say 903, we don't write a 9 and then write a 3. We have a 9 in the 100 spot, a 0 holding the 10 spot, and then a 3 holding the 1 spot. If we want to perform polynomial divisions on these polynomials, we need to look at the highest degree, degree 4. If we were to multiply things by x to get to degree 4, we would have gone through degree 0. Then we would have times by x, we would have got first degree. Then we would have times by another x and got second degree. Then we would have times by another factor of x and got a third degree term, which is missing here. Then we would have gotten a fourth degree term. So if we're not careful, we can do it without putting in anything special, but your stuff is not going to line up properly. If you want it to line up properly, like it does when you're doing numerical division and hundreds goes in the 100 spots and tens in the 10 spot, then you need to hold a spot for every degree. So we would have 4x to the 4th, and then probably the easiest thing to do is there is no x to the 3rd term, but you want one there just so that if x to the 3rd pops up, there's something to line it up with. So we just write plus 0x to the 3rd. And we call that a 0 placeholder. I haven't changed the polynomial. I have 0x to the 3rds. It is 0. It is okay for me to write it like this. I haven't changed any value, but I've given a spot where something could go. Okay, so our setup looks like this. Now, it's a little more difficult to decide what we're multiplying by because we're using something a little more complicated, and we're going to use the first terms to our advantage. So basically, can you multiply 2x by something that would then make it be something to the fourth power? We can, okay? So the question is which one? There's lots of choices. But what we want to do is notice in the division problem that we did before, as we went through the problem, it kind of moved to the left like this. And it moved to the left because we really made sure that whatever we chose would take out that highest place in our number system and leave numbers in the lower place values until we were all the way to the end of our place value system, okay? So we want to do the same thing here, but with the degrees of the polynomial. So we want to exactly match the highest degree term however possible so that that one gets canceled out, and then we'll deal with the next degree, and then we'll deal with the next degree till we can be done completely with the problem, okay? So at first, when I make my decision about what to choose, I really just focus on first terms. What would I multiply 2x by to get it to look exactly like 4x to the fourth? 2x to the third power. So I'm going to choose 2x to the third power. Now, you don't have to write it over the second spot, but does anybody know why I chose to write it over the second term? Not because they're both x cubed. That's just coincidence, but good guess. What's going to happen in the next step of my algorithm? Marcus?
Well, if you want to align with each other, that makes practical sense.
I do want it to align with each other, but I don't need this to align with this. I need the stuff down here to line up with these. Natalie?
The next one you're going to do is -5x squared. Calculating -0x to the third.
These are all good ideas, but no, I still need to pay attention to the third term. Right. So the next step is to multiply this by this, and when I do that, how many terms am I going to get? 2. So when this multiplies this, I'm going to get 2x cubed times 2x, which makes that 4x to the fourth. But I'm also going to get 2x cubed times -1, which makes -2x cubed. So do you see why I put it over the second thing? More because this has 2 terms. So when I choose something, I'm going to make something with 2 terms. So that's generally why they do it. It doesn't really matter, okay, because you're just getting your answer across the top. But when you keep seeing them do this, I just wanted you to understand why they lined it up that way. Now, after we multiply, what does our division algorithm say to do? Subtract. Now, again, now that you have polynomials, that's a little bit messier. You are subtracting this entire quantity from the thing above it. When you're subtracting an entire quantity, what do I have to be careful about? The signs, okay? This isn't just 4x to the fourth minus 4x to the fourth, and then I do what I see here. This negative goes here as well as here, okay? So I am subtracting this, but this -2x to the third is actually going to be treated like a positive in order for me to perform that subtraction. So these cancel out. That's what I wanted to happen. That's what I want to happen in the division algorithm. I want to move to smaller degree terms. And then here I'm going to be left with 2x to the third. And just like in our division problems, I'm going to bring down the next place, which is the next degree term in my polynomial. And then I just start the process over again. What would I want to multiply times 2x to obtain 2x to the third? X squared. So x squared is what I choose. So I write that here. And then I'm going to take that and multiply it times this polynomial, which means to distribute it to each piece. So I will have x squared times 2x, and I will have x squared times -1. And again, after that, I am subtracting. And so I cannot forget that that affects all of the signs of this polynomial that I've come up with. So that this 2x to the third is negative, and that this one's going to appear positive. So those cancel, which is what I wanted. Then I would have -4x squared. I would bring down the 2x. What would be the next term I'm going to choose as my part of my answer? -2x. Good. Okay, because if I choose -2x and I multiply it times 2x, I get exactly -4x squared. And then -2x times -1 is positive 2x. And this doesn't always work out like this. This just happened too. So when I change these signs, this becomes positive, and this becomes negative, and both of these cancel out. Okay? That's okay. That just means I have 0 x's left from that. And then I would bring down the 4. Now, you know how before, when we were doing our division problem, we said, does 7 go into 6? And we said no, so we moved on to 63, right? In polynomial world, we look more at degree. Is there any powers of x that you can multiply x to the first power by and get just 4? No, because it lowers the power, so that doesn't make sense. So at that point, you know you're done. If you're trying to make something of a lower degree than what you already have, okay? And the reason ours would be lower degree, it wouldn't be if there was something with an x here. But because ours is 0x, it's like that doesn't exist and we just have 4. That's how we know we're done, okay? So our answer to the division problem is 2x minus 1 goes into that polynomial, 2x to the third plus x squared minus 2x with a remainder of 4, which we write like a fraction. So this means add on this fraction that says 4 was left over when I was dividing by 2x minus 1. Just like if 3 was left over when you were dividing by 7, you called it 3 over 7. Okay? 4 was left over when I was dividing by 2x minus 1. Okay? Any questions about the process? So this is the quotient. The quotient is the entire answer when you divide. Okay? The remainder was what? 4. That will be important to tell us some different things about our polynomial later. If something is a factor of something else, what is the remainder when you divide those things? Is 2 a factor of 6? What is the remainder when 6 is divided by 2? No, the remainder, 0. Is 5 a factor of 6? No. How do you know that? Because when this 6 is divided by 5, there is a remainder, right? It doesn't go in evenly, as you guys like to say. All right, so we're going to race and do a division problem real quick. I know you guys are excited. So we're going to go ahead and take this and divide it by x minus 2. Okay, so you guys are going to try and beat me. I'll give you a head start. Go. All right, I'm done. All right, so who wants to learn what I just did? So because division has this concrete repeated algorithm, there is a way to take out all of the x stuff and just numerically figure out what's going to happen because you just have this repeated process of what multiplies to make this and then subtracting and whatever. So we are going to do what we call synthetic division, okay? Synthetic as in like not pure, right? Just kind of taking it and turning it into the process. So what you basically do is you take what you're dividing, so 6x cubed minus 19x squared plus x plus 6. You just take the number parts, the things you'd have to figure out what times this equals that number. So 6, negative 19, 1, and 6. And then you're dividing by x minus 3, so you take the 0 of that factor. So x minus 3, if you tried to set it equal to 0, what would you get for x? Positive 3. So I'm going to see what positive 3 looks like when I do this. And this has to do with the fact of how you change signs and stuff like that in division. Then all you have to do, this is just a process you have to memorize. It's synthetic division, right? It's just an algorithm. You drop down the first coefficient, and every time something shows up underneath this line, you multiply it by that 0 that you picked out, the number you put in the box. So like 3 times 6 is 18, and then every time you fill up a column, you add it up. So negative 19 plus 18 is negative 1. Okay? Negative 1 times 3 is negative 3, and I add those two things up and I get negative 2. And negative 2 times 3 is negative 6, and I add those things up and I get 0. Now, this is your remainder, okay? That's the last thing you would have had left in your division process, okay? Which means if you work backwards in the polynomial, if that's the remainder, then this one is the constant, right? 0 degree of x. Then this one is going to be x to the first degree, and the next one would be x to the second degree. And we can do that as long as we're consistent about always writing it in standard form and always making sure there's something to represent every degree. Okay? So our answer here is that we would have 6x squared minus x minus 2. Okay, with no remainder. Okay? What's that? Yeah, it probably does, but you probably have to think about like 100 spot, 10 spot, instead of like x to the second power, it would be like 10 to the third power. If you want to come in one day, we could actually do that. I'll think about that tonight, and I'll show you guys how it could work with regular numbers. I think you could. Okay, so the next one is a little bit different for 2 reasons. The polynomial we're dividing is missing an x to the third power. And we're dividing by something that has a coefficient. That changes it a little bit, okay? However, 4x to the fourth minus 5x squared plus 2x plus 4, okay, is being divided by 2x minus 1. Now, this process doesn't work with this coefficient here, okay? However, I could rewrite this and get the coefficient to cancel out if I factor out the coefficient I don't want. Okay, so if I factor out the 2, what does what I'm dividing by now look like? X minus 1/2. Okay, but if I want to be able to cancel out the 2, and why am I allowed to do this? Let's see. 18 divided by 6, okay, is 3. But that's the same thing as 9 divided by 3, right? If I just reduce the fraction, and I'm able to do that because if I think of 6 as 3 factored out with a 2 left over, and I think of 18 as 3 factored out with a 9 left over, I can cancel those, get a reduced version of it, and the division problem still comes out to the same result. So I can do this here. The numbers don't look as pretty because you have to deal with some fractions, but it takes away having to do the long division process. So you just kind of can pick your battle. So if I factor out a 2 here, this is only going to work for me if there's another 2. So I'm going to like forcibly make a 2 also there so that they cancel out. And I have a new version of the problem that I know will work out the same way. Natalie? Oh, sorry. Oh. 18 divided by 6. Oh, gotcha. If I do it that way, sorry. I just realized. Better? Okay. Thank you. All right, so I'm going to factor a 2 out of all of these, even when it looks a little ugly. And when I say when it looks a little ugly, that's going to be like at the 5, right? When I factor a 2 out of here, so I get 2x to the fourth minus 5 over 2x squared plus x. But now these 2's cancel out, and I can do this other division problem, and I can now do it this way because I've set it up with a linear factor. So this does have some limitations. You can't do it if you have like x squared plus 3x plus 2 as your divisor. If you're trying to divide by something that has a higher power than x to the first power in it, you have to just do long division. Okay? So this only works when it's linear and the lead coefficient is 1. So we can always make the lead coefficient 1. But we can't make something linear that's not already linear, okay? So now when I set up my division problem, 1/2 is going to be the number in the box because it's like what I would get if I set x minus 1/2 equal to 0. The coefficients are going to be 2, because now I'm looking here, right? I factored this out. I'm going to finish this problem. 2, x to the third is missing. You need to put the 0 placeholder here, especially when you're taking out all the x's and you just have these random numbers. They're not lining up right if you don't represent every power of x from your highest degree down to your constant. So 0, then negative 5 over 2, and then 1, and then 2. Okay? And then we would go through the same process. So we'd drop down 2. 1/2 times 2 is 1. Okay? We would add this column up. 1/2 times 1 is 1/2. We would add this column up. That's the same thing as negative 2. 1/2 times negative 2 is -1. We would add this column up. And 1/2 times 0 is 0, and we would add this column up. Just make sure I didn't make any mistakes. Say it again. Are you okay? It's because I multiplied 1/2 by 2. All right, so remember, this is the remainder, right? So this one has a remainder. And then I go up into read. This is constant x squared, x cubed. It should make perfect sense. You divided something that had x to the 4th power by something that had x to the 1st power. You should have something left that has x to the 3rd power, according to how exponent rules work, right? So my answer here is 2x to the 3rd plus x squared minus 2x plus 0, but I don't have to write that. And then I have this remainder of 2. Now, it gets a little tricky. You're not going to always see the answer written this way. This is a viable answer, but you know the whole fractions within fractions, radicals in the denominator, stuff like that. People generally, it's kind of like grammar rules in English, right? It's just like frowned upon to write it that way. So you may see this written where they said, oh, we don't want a 1/2 in a denominator of a fraction, so we'll multiply the denominator of the fraction by 2, but that forces us to also multiply the numerator by 2. And so then they might write the answer as 2x cubed plus x squared minus 2x, but write this new version of this remainder that doesn't have a fraction within a fraction, like 4 over 2x minus 1. Okay? So long division process, same algorithm you've always known, okay? But just being careful with how to do it with polynomials. And then new synthetic division process that we can use when we're dividing polynomials by some factor where it's only to degree 1, okay, as an x to the 1st power, and we make sure it has no lead coefficient before we start the process. Does that make sense to everybody? Okay, so this is enough for you guys to do.